Today's topic is wave motion in strings. You might have experience if you take a long rope and if you snap it up and down once, then what happens? A ripple is created. And even if you don't do anything more, then what happens is, with passage of time, you will see this ripple progressing. You're not doing anything. This ripple is just progressing in this direction. Now, if you start walking along the wave with the same velocity as this, you will see that this is this portion or the pulse of the wave is stationary. Nothing is moving. Is that so? No, it is not like that. It appears that the wave is fixed, but it is not so, because when the wave is here, the particle involved are this one, this one, this one. Let's say P1, P2, P3. When the pulse is here, now it could be P5, P6, P7, and if it goes much further, it could be P5 will be here, P6 will be here, P6 will be here, P7 will be here, and there will be new particles. For example, this may be P8, P9, P10, so on and so forth. So what you see, it is not the particles, is the same particle which are going forward. No, not at all. So first thing is, particles don't move. If we take this direction as X, don't move in X direction. And if we take this as Y direction, the particles always move in Z direction. Sorry, Y direction. If you see the particle here, what it will do? It will go up, it will go down, cross the mean position, come back, and like this. It will keep on doing it, but it will keep on doing it at the same X position. It will not move from this position. Because all the particles behave like this, it appears that the pulse which was generated is moving in this direction. Now, as we have seen, that the particles actually move up and down in this direction, while the wave seems to be progressing this way. The moment the particle is perpendicular to the motion, direction of motion of the wave, that is why it is called transverse wave. In a transverse wave, the particle moves in a plane. They move in a plane which is perpendicular to the motion of the direction of wave. This is the direction of motion of wave. And this crest, with whatever velocity it moves here, is called the velocity of wave. Right? Okay. Now, Let's see how this wave can be represented. This wave can be represented as a function y, which involves x and time, is given as a sine omega when the sine of t and x are opposite to each other. This means the wave is moving in positive x direction. Right? Now there are many, if we see the actual wave here, A is the amplitude, the maximum displacement. This is our A. This is our direction of x. This is our y. At any place x, the displacement is y, which is represented by this equation, and omega is the angular velocity. V is the speed of the wave. Okay. Now, let us see the reflection of waves. We've seen a disturbance which was generated. Now, if our string was very long, it will keep on moving in this direction. But what happens if it meets a fixed point? Then what happens is this progresses, comes here, here, here. Finally, it comes here. And then, since it cannot go any further, it reflects. And in reflection, what happens is it goes like this. It goes in negative x direction. And the equation will change. The equation becomes y, which is a function of x and t, is equal to a sine omega t plus x. When the sine of t and x are same, it means the wave is moving in negative x direction. Now let us see other ways in which the wave can be reflected. Let us say we have a rope which is thin here and very thick here. Then what happens is the wave which was going like this, it progresses here. And when it hits this interface, what happens is the wave inverts. A part of the wave is inverted, like here, and moves in negative x direction. This is x direction. This is y. And part of it doesn't reflect and just proceed further. And it keeps going like this. This is when this portion is thin string, and this portion is from here onwards is thick. At the interface, the wave, part of the wave will reflect back and part of the wave will proceed further. The part of the wave that proceeds further doesn't go under any chain, but the one which gets reflected gets inverted and proceeds in the negative x direction. Now let's take another case that our first portion is a thick one, and then we have a thin wire. This is thick, this is thin. Then what happens is, any disturbance that was happening, again what happen? Some part of it will this is the interface of thin and thick string. The one which a part of wave gets transmitted, it will get transmitted without any chain. And the one which gets reflected will get reflected without any phase change, which means that if we take another instance, if we see the backward journey will be like this. It means when the wave travels from thick to thin, neither in the transmitted portion nor in the reflected portion, the wave changes its shape. The shape of the wave remains same. Now, next topic we study is standing waves. What are standing waves? Standing waves are waves in which we see nodes which always remains at rest. That is, for them y is 0. And it gives us the impression that the wave is not moving anywhere, it is standing. For example, the standing waves could be now these particular points which don't move at all at any time are called nodes, and the wave looks as if it is standing. It is also called stationary wave. How they are produced? They are produced by two waves, one wave going in the positive direction and a reflected wave going in the negative x direction. Let's see their treatment. The one going in positive x direction can be represented at, we have already seen, y is equal to a sine this is going in this direction because the sign of x and the sign of t are opposite to each other. So this is proceeding in positive x direction. Let's take another wave, which is a reflective wave. When the sign of x and sign of t are same, this is a reflective wave going in negative x direction. Now, if we add them together, is a sine omega t minus kx plus a sine now if you see the wave going forward and the reflected wave going backwards, they have the same amplitude. same angular velocity. Okay. And same k. K is called the wave number. Now, if we do some trigonometry, this will become 2a cos kx into sine omega t. This is the amplitude of the combined wave. At any point x. Now, if you see the pattern of this behavior, this combination, we will see that there are places called nodes. They are the places where, what are nodes? Their amplitude is 0, which means if amplitude is 0 means this was our amplitude, 2a cos kx is equal to 0, which means kx has to be an integral multiple of pi by 2, pi by 2, 3 pi by 2, and so on and so forth. So nodes will be formed when our kx is equal to, if we generalize this, this becomes half pi, where n is starting from 0, 1, 2, and 3. This is the condition of our nodes. There will be places which have the maximum displacement. They are called antinodes. Now, in this wave, these are called nodes because amplitude is 0. And these points are vibrating with maximum amplitude, and these are called antinodes. So antinode is a place where y is maximum. And when is y maximum? Again, if we see our equation, this one, when will this function be maximum? When this value is 1. And when is this value 1? This value is 1 when this is 0, or pi, 2 pi, etc. So we can generalize that when kx is this value is n, where n varies n pi, where n is equal to 0, 1, 2, 3. This is the condition for antinode. Now, if we look at this equation, what is this? if our sine omega t is 0 for any x, because it doesn't involve x, it involves only t, then what will happen? All such points, all x's will be at rest, which means the wave will see looks to be stationary, because here y is 0 for all x. Now let's study some difference between standing wave and transverse wave. This is our transverse wave. This is our standing wave. First thing is disturbance propagate with fixed speed. And if you have this wave, or let us say we saw this hump will keep moving with a fixed speed. And it doesn't hit any obstacle if it is fairly long string, keeps going. Whereas standing waves, the region is confined, because for standing waves it needs to reflect back. It come here and then it just reflect. So it has to go backward and forwards. So the region is not limitless. The region is confined. Second thing is no particle is at rest all the time. Okay. But we have seen in standing waves, particles at nodes are always at rest. No matter what the time is, they will always be at rest. Third thing is at no instance all the particles will cross mean position no instance all the particles will cross mean position together, or there will be no instance when all the particles will be at mean position. Where in case of standing waves, all particles cross their mean position together. Okay. Fourth comparison is phase of all all nearby particles is different. But in case of standing waves, all particles between two consecutive nodes reach their maximum y together, which means that if we take this, then this is the part of the wave between two nodes, these two nodes. The maximum displacement of this particle is so much. Maximum displacement of this is so much. Maximum displacement point here is this. They will reach their maximum position together. So together they will go up. Together they will come to the mean position. Together they will go to the minimum position. Together. So they are all in same phase between two consecutive nodes. Now let us see in which form, different forms in which standing waves can be formed. We know for making a standing wave, the string has to be fixed at both the ends. Now, one mode of vibration is that it goes like this. Second could be it goes like this. Third could be like this. They are all clamped at both the ends. And let us say if this is the length of the string, then what happens is that what is lambda? This is half lambda. So lambda will be 2L. What about here? There is full wave, so lambda is L. Here, there are 1.5 wave. So 3/2 lambda is equal to L, or lambda is equal to 2/3 L. So condition of resonance is resonance means when this or this pattern is formed is when L is equal to okay. Where N is equal to 1, 2, 3, 4, and so on and so forth. When N is equal to 1, you get L is equal to lambda by 2. L is lambda by 2. Here L is equal to lambda. Here L is equal to 3 by 2 lambda. So N keeps changing and you will getting different overtones. For N is equal to 1, the wave we get is called fundamental node, fundamental wave, or node, or frequency. L is also defined as N by 2 and then lambda. Lambda is nothing but V velocity by frequency. And in case of standing waves, we know that velocity of a standing wave is given as force by mu under the root. This is velocity of transverse wave. Velocity means with what velocity that hump we saw earlier is moving in x direction, this direction or this direction, doesn't matter. And F, all these cases vibrate when the string is stretched between the two. If the string is stretched, obviously there will be tension. So this is the force of tension, and mu is linear mass density, linear density. Means, for example, kg per meter or kg per centimeter, whatever. So velocity will be given by this formula. So if we use this formula and put the value of V here, what we get is L is 1 by 2 mu F by mu. We've taken N as 1. When N is 1, we have already seen that this wave is called fundamental node. Fundamental frequency, and this frequency we denote as mu naught. As we have seen, standing waves are formed by interference of two waves, one going in positive x direction and a reflected wave going in negative x direction. Y1 we represented as a sine, and the reflected wave was let us say there is a phase angle between these two. Now, if we add these two up, means what happens when these two waves, one going in this direction, one going in this direction, interact with each other, we call it superimposition. superposition. So the result will be addition of y1 plus y2, which is equal to now if we do some calculus, our y is this is our simplified form. Now we know for standing waves, the boundary conditions are that y is equal to 0 and x is equal to 0 for all time, for all t, meaning whether we take this wave or whether we take this wave, what is common is that at x is equal to 0, y is, this is x direction, this is y direction. At x is equal to 0, y is 0 at all times, whether you take this wave, or this one. For all of them, at x is equal to 0, y is 0 at all times. This is one boundary condition. What is another boundary condition? Same condition applies at the other end also, which is y is equal to 0 at x is equal to L for all times. These are the two boundary conditions. Now when we say all times, so we take a term which is independent of time, which is this one. So what it will mean is, should be 0 at all times, right? This is at x is equal to 0. When we put x as 0, what happens is which employs delta is 0. So we can rewrite this equation as because this phase angle is 0, as we have seen it here. Another boundary condition was at x is equal to L also, y should be 0. Which means that this is 0 for x is equal to L, which means that sine KL is 0. And what does this mean? This means that KL should be multiple of pi, etc. Or simply we got n pi, where n is equal to 1, 2, 3. we know lambda is equal to Vt. This is the velocity. This is time period. This is wavelength. This is also equal to V by naught. This is the frequency. Now our L becomes mu by 2. So mu is equal to Vn by 2L is equal to, and we substitute the value of V. We know V is F by mu under the V. So for fundamental frequency, we know fundamental frequency we denote as nu0, and here n should be 1. So it becomes this is the formula for fundamental frequency. Similarly, if we take the value of ns2, then it becomes 2 by 12. This becomes and so on and so forth. We have already seen for standing waves, y is equal to 2 pi before we do this, let's examine our waves again. This one. We have seen that we can write our formula as or both are similar. Now, what is K here? K here is if we compare this and this, our K is nothing but this will be omega here also. So K will be omega by V, which is equal to 2 pi by, and velocity is time period times Hmm. This is our omega. This is our V. And this is also velocity time period is lambda. So K is 2 pi by lambda. K is called the wave number. Okay. Now we have seen here lambda, here is 2L. First overtone or second overtone as we call it is L. And what will be the value of K here? K is 1 by L. K is right. Now, if we instead of we rewrite this equation in our original form, which was y is equal to 2a sine kx. Now what we do is, we have seen k is equal to for example this, you see that k is equal to n pi by l, where n will vary from 1, 2, 3 likewise. So what we do is, instead of kx, we substitute the value of k, which is right. Now we know that nodes will be formed. What are the conditions for node? Y is equal to 0, at x is equal to 0, one condition, yes. Also 0 at all these places. Or at boundary conditions of each of these types, which is this being IR. Now what we do is, we do some treatment for a fundamental mode. In fundamental mode, n is equal to 1. So our equation becomes now what we see here, y will be 0 at x is equal to 0, right? And this is also at 0 when sine of this is 0, and which is pi, 2 pi, etc. This is the conditions for nodes. For fundamental nodes, we only restrict ourselves to first value. So here what we'll have is or x is equal to L. These are the two boundary conditions that y0 at x is equal to 0, which was at this place, x is equal to 0 here. And second boundary condition is x is equal to L. Here also our y is 0, which is this place, x is equal to L. This is our fundamental node. For antinode, y is supposed to be maximum. And when is this function maximum? This function is maximum when this is equal to sine of this is 1. Sine of this is 1 means this angle should be equal to pi by 2, which implies our L is our x is L by 2. So our node will be at midpoint of total length, which is here. This is x is equal to 0, x is equal to L. This is the midpoint. We see here at this point or this point, this is our antinode, where displacement is maximum. Now, can we produce waves only by clamping a string between two supports rigidly? Not necessary. Then we can produce it by clamping at only one place and leaving the other end free. So if we do this, what are the modes in which the string can vibrate? One is it vibrates like this. Second is this is second way. Third could be and so on and so forth. Again, this is our total length of the string. This mode is fundamental mode. This is the overtones. These are all overtones, or they're also called harmonics. Now, if we take our equations, once again, the same one, y is equal to now boundary condition for our waves which are clamped only at one end is what? That y is equal to 0 at x is equal to 0. Obviously, x is 0, x is 0, x is 0. Since they are clamped, they cannot move. So y has to be 0. And second is y is maximum at this end, this place, this place. This place is what? All or else. And x is equal to L. At this condition, what we get is node, because y is 0. And when y is max, what we get at this position is called antinode. So this, and this are nodes, whereas this position are because here the displacement is maximum. This is the displacement. Now for antinode, what will be the value of kx so that this functions become maximum? This is this means sine can take a maximum value of plus and minimum value of minus 1. So we can say that for antinode, sine kx is equal to plus minus 1, or which means that we get we know that we have antinode at x is equal to L. So we will have an antinode at x is equal to L. If sine kx is supposed to be plus minus 1, then at x is equal to L, KL should be equal to for n is equal to 0, 1, 2, and so on and so forth. You can write this also like this. If we substitute the value of k as so, and this equation becomes n pi, this is k This can also be written, K can also be written as K is 2 pi lambda. So our this equation becomes pi, or this gets cancelled this way. 12 by pi, 12 by lambda is equal to okay. This was the treatment for Antinode. Because at this condition, sign will be maximum. Now, for a fundamental mode, frequency is given as this is equal to and we know that this is nothing but velocity of the wave. So in fundamental node, our frequency becomes velocity divided by 4L. Now, while talking about a wave being fixed at one end and free at the other end, a similar behavior will happen if we clamp a string which is thick at one portion and then it is joined by a thin string, and even if they are clamped at both ends, this is the thick string, this is the thin string, the wave will reflect. This thick string will behave like a string clamped at one end, which is this end, and since it is not clamped here, this end is free and other end is free. So it will exactly behave like as if you have length L, string of length L clamped at one end and free at the other end. It will exactly behave like this, even though it is connected by a thin string which is clamped at other end also. Now one more topic was what is the power transmitted in a traveling wave. Because when a wave goes like this, some energy is required to propagate it. So what is the amount of energy required to propagate it? Is given as omega square this is the angular velocity, this is the amplitude, this is the tension in the string, and this is the velocity of this can be further simplified as this is the linear density of string, this is the wave velocity, this is the amplitude, and this is the frequency of oscillation. So this is the power which is transmitted along a string by a sine wave.